Okay, let's get started. So, yeah, I uploaded homework 2. So just send an email or announcement, right? So if you didn't receive it, just let me know. Okay, it will be due on March 13th. Okay. And for the midterm, probably it'll be in the end of March or the beginning of April. Okay, and it'll cover everything up, including up to chapter 5, and also cover a little bit in chapter 7, I guess. Okay. All right, so let's see what we covered in our last lecture. So in last lecture, we focused on the Kraft inequality. In particular, we talked about the more general version of the Kraft inequality, which is for the uniquely decodable code instead of only prefix code, right? Okay, and we didn't talk too much about the construction, right? So we'll leave that for today. And then we talk about the optimal codes, right? Okay, let's see in detail. So here is the definition. So here is the Kraft inequality for the prefix code, right? In particular, here we focus on the binary case, right? So this is the inequality, and that is necessary and a sufficient condition for the prefix code, okay? And for the construction, we just say, okay, so we can use the code tree to construct it, right? Today, we're going to see how we are going to construct it exactly. Okay, and then we shift to the uniquely decodable code, right? And here we consider a more general case where it's a DRE code, okay? And this is a Kraft inequality, so which is a direct generalization of the Kraft inequality for the prefix code, right? They are basically identical, okay? They are totally the same. And also, it is sufficient and necessary condition, right? And we prove that, the proof is quite tricky, right? So basically, we need to write down a formula in 2 ways, right? And then use some inequality to prove it. Okay, so so if you don't recall, then just take a look at your lecture notes. Okay, and the one important implication of this is that, so yeah, because for the uniquely decodable code and the prefix code, they have exactly the same Kraft inequality, right? So this basically means that by using the prefix code, so we do not lose anything, right? So which is more constrained code, right? So I have more, it's more constrained for a prefix code because we need to guarantee any code is not a prefix for any other codes. Okay, it's more constrained, but so it turns out that we do not lose anything in terms of the, the length of the code. Okay, so basically in practice we can just use the prefix code if we like. Okay, and then we focus on the optimality of the code, okay? So basically what we can show here is that we consider the block code, which is an NFG code, right? And we also consider a prefix code, okay? So it is kind of obvious that, this inequality is true, right? So because before we show, even if we allow an epsilon error, this inequality is somehow true, right? So this is true, but the important thing here is that the equality can hold actually, right? It can hold when the distribution of the sourcing both satisfy this equation, okay? And when this equation is not satisfied, then the equality may not hold, okay? And then what we do here is that we take a ceiling of this, right? And obviously that is less than, or there's a minus here, I lost, so missed. So it is less than or equal to minus this number plus 1, right? Because it's a ceiling, okay? And we can show that. So basically, we lose basically a constant of 1 over n, right? When n goes to infinity, so this will disappear, right? But in practice, so this n is never infinity; it's finite, right? Therefore, so this may not be negligible, right? Because know that. So this is the average code length, right? It's ln over n, right? So basically, in practice, if n is not very, very large, right? If we multiply n here, right? So this could be, not negligible, okay? So which is, Yeah, we're gonna probably see an example today or next lecture, okay, on why it can be bad. All right, so today, we're going to continue talking about this. This is our lecture number 20. Okay, today we're going to focus on two types of code. One is Shannon code. Okay, and the other one is called Huffman code. Okay, so those are the two important codes. We're going to see other kind of code later as well. All right, let's start with the Shannon code. So this is probably the most straightforward code, right? The idea of the Shannon code is from the Kraft inequality, right, as we just seen. So basically, the idea of the Shannon code is that we know the self-information. Yeah, let's use a small x here. Equals to this, right? So this is self-information. Okay, remember the meaning of this guy is nothing but the number of bits of information needed to resolve the uncertainty of x. Okay. Therefore, it makes sense. Kind of, we just use this number of bits to encode the symbol x, right? So it's kind of straightforward, even if we do not introduce you the Kraft inequality and so on. So probably we want to use this as the length of the code for symbol x, right? Because that is the uncertainty. Okay, so in general, since this number may not be an integer, so we just use a ceiling. Right, and so here, so when we mention Shannon codes, so we want to use this code length for sure, right? But we want to construct a prefix code. A prefix code. Okay, so why we can construct a prefix code? Yeah, because the theorem we just learned, right? Because it satisfies the Kraft inequality, right? If that inequality is satisfied, then we can construct a prefix code, right? And we just show that, okay, for the prefix code, okay, we can pick the length as this number. Okay, so that's the logic, right? Hopefully that makes sense to you. So now, because if we pick this number, we're sure that the inequality of the Kraft inequality the equality in the Kraft inequality will hold, and we're good, right? But now we're picking this number, so which is slightly different compared to this, right? So we need to double check whether the Kraft inequality in this case is satisfied or not. Does that make sense? All right, let's double check it. Okay, so yeah, let's write it down first. So we say if the Kraft inequality this less than or equal to 1, then there exists a prefix code having code word length as this. Okay, so then basically the only thing we need to kind of show is, so this inequality will hold if we pick, this code length, right? So let's see how we can do that. Now let's double check it. So basically for the Kraft inequality, so that is this, right? So we just need to plug the length in, right? So that's minus log. So because we're using a DRE code, so in the log we just take a D here, okay? Px. Okay, so now what we want to do is that we want to get rid of this ceiling, right? If we get rid of the ceiling, we can see that this guy will just equals to 1, right? So we want to get rid of this ceiling. So now the problem is that when we get rid of the ceiling, so we get an upper bound or lower bound, right? So we have a minus here, right? So this guy is in the denominator. If we get rid of the ceiling, then in the denominator, so we get something bigger or smaller.
Bigger in the denominator.
Yeah, in the denominator it's get wait. In the denominator it's bigger than this. You want an upper bound, something wrong here. Okay, let's see. Yeah, let's. Okay, so it's the 1 over d log this guy, right? So now if we get rid of this, so this guy will become smaller, right? Right, so we remove the ceiling, so this is become smaller, right, in the denominator, right? So this guy, so this is smaller or less, is smaller than or equal to this, right? Okay, so if that's true, then we do have upper bound, which is good. So we have upper bound, so that is d minus this, okay? So that equals to d log d px, right? And then this becomes what? Px, right? I have a d log base d here, right? Then that equals to 1. Okay, then we show that. So this guy is indeed less than 1. Right? Okay, so then we're good. So yes, good news, right? So the Kraft inequality will hold, so we're fine. Yes?
When we're taking the upper bound of a negative value, like minus 3.5, the upper bound is minus 3, right?
Oh, it's a positive number. It's minus log, here is a probability.
Okay.
Yeah, so we can move this inside.
Okay, I see.
Yeah, very good. Okay, so now we know there exists a prefix code, right? So now we just need to construct it. Let's see how we can construct it. Okay, so now, so we never rigorously showed this before, right? We give you some example, it's sort of true. So now let's prove it, right? The proof of the existence of prefix code. Okay, so let's see how we can prove that. Yeah, again, so the idea is to use the code tree, right? So basically the code tree is like, we want to have a, have something like this, right? We have a tree here, right? And then, the tree may, have something like this, and so on, right? We want to construct this kind of coding tree. Okay, now the problem is how to construct it. As you remember, so when we prove the binary, the prefix case, so we consider a binary, this coding tree, right? So basically before, if it go up, we'll give a 0. If it go down, we'll give a 1, right? But now we need to consider, so in order to show this kind of tree always exists, so what is the key part that we need to guarantee? Right, let's think about it, right? Maybe you can think in this way. Yeah, let's consider the simplest case, okay? So let's say when there's only like one layer of the tree, okay? Let's say, okay, so if we consider the code length start with length 1, okay? Right, if it's a binary, so, and if we have only length 1 code, then there is a 2 possibility, right? 0 and 1, okay? And if we use 0, and the left is 1, right? And then what is the total number, maximum number of length 2 code?
For binary trees.
Yes.
4.
Wait. Let's say, yeah, remember, let's say the first step is that, let's say we have a 1 length 1 code, okay? For example, like 0 here, right? And then we have 1 left,
Okay.
1 branch left, right? And now what is the maximum number of length 2 code? So we have 2 possibilities here. How many?
Length 2 code?
Yes.
Number?
Uh-huh.
3, because you can't do 4. Because
2.
You can't, 2?
Yeah, because this one is done, right?
Oh,
And
okay,
now,
like the more,
yeah, and now for the length 2 code, we can only have 2 at most. Do you see the problem? So basically, we need to guarantee, the total number of branches is enough, right? If we want 3 length 2 code, then it's not okay, right? So that, besides this length 1 code, the total number of length 2 code has to be satisfied, okay? So at most, I can give you 2. If you want 3, then you're doomed, right? There's no way. Okay, so basically that's the key, okay? And how do you know whether this number is okay or not, right? How can you know that? How do you know whether this 2 is enough? Because what we learned, craft inequality, right? So that gives you the bound, right? So basically, the only thing you need to check here is that, okay, whether these 2 satisfy, or whether these 2 satisfy your craft inequality. If it's yes, then you're good. If it's not, then you're not good. So that's basically the proof idea. Okay, so I know it's not clear yet, so yeah, let's talk about details. Okay, so I'll probably remove this. Yeah, okay, so basically what we're going to do is that we're going to consider length by length, okay? And we kind of did that before when we show the craft inequality of the uniquely decodable code, if you still remember it, right? So basically what we want to do is like this. So we write down this craft inequality formula, right? And then we rewrite it, right? So if you remember when we showed the upper bound, we rewrite it. Now we do the summation based on the length of the code, okay? From length 1, length 2, length 3, and so on, right? So basically we're going to do the same thing. So we write this as summation over I and Ni times di. Okay, and what is Ni? So this is basically the number of x, the source, such that Lx equals to I. Okay, sum over length 1 code, length 2 code, length 3 code, and so on. That makes sense? Okay, so now what we consider is that, okay, so now let's start from length 1 code, okay? So let's say length 1 code, so the number of that is n1. So can you tell me what is the upper bound of n1? So what is the maximum number of length 1 code you can construct?
D.
Yeah, D, right? Because it's DRE code, right? But D length is 1, right? But the total number is D, right? Yeah, for example, if D is 2, then the length 1 code you can construct is 2, right? It's 0 and 1, right? If D is 3, it's 0, 1, 2, then you can construct as 0 and 2, right? 3. Is that clear? Okay, great. yeah, this is very important. So from here, we can get a very nice inequality, so which is n1 times d minus 1 is less than or equal to 1. Right? What is that? Is that familiar? Or this? Right, so basically that's the Kraft inequality, right? For if we only consider one code, length one code. Okay, so now we need to extend it, right? So now let's assume this. Let's draw one more here. So let's say, okay, so this is n1. Okay, so I have n1 of length one code. Okay, and then the maximum number of this children left is d minus n1, right? Then the total number is still d, right? Right, so now let's consider the length 2 code. Okay, so can you tell me what is the total maximum number of length 2 code? Okay, so now we consider the maximum, there's an I here, right? There's the maximum number of length 2 code. Okay, or means n2, right? So what is the maximum number of length 2 code? Say it louder.
D minus n1 times d.
Very good. D minus n1 times d. That right? Yeah, because we have a d minus n1 here, right? And each of them can have d branches, then multiply d. That right? Okay, so now let's check whether this satisfies the Kraft inequality or not. Okay, so now let's write down the Kraft inequality. Okay, Kraft basically this one, right? It tells you that n1 times d minus 1 plus n2 times d minus 2 is less than or equal to 1. Right? Yeah, this is a Kraft inequality, right? So we just use it here. Okay, and now, yeah, let's manipulate, right? Let's multiply d squared on both sides. So this n1 times d plus n2 less than or equal to d squared, right? And then let's solve it. So n2 is less than or equal to d squared minus n1d, right? That is d times d minus n1. Yeah, let's write it more clear. Don't have lots of space. D minus n1. Can you see it? Oh. Yeah, what should I do?
Can you lower the projector at all?
No.
Just scroll down.
Yeah, no problem. Let me make it higher. I have a lasso tool. Where is it? Oh, here.
I think you can just scroll down the page. Oh no, I guess not.
Yeah, I will move it up a little bit. Yeah, can you see it? Okay, great. Yeah, then I have more space, right? So I can write it bigger. Let me write it bigger. Equals to d minus n1. Right, and now we can see that, so this guy and this guy is exactly the same, right? Therefore, so we have enough number of leaves here. Okay? And they're all good. It means that we can construct a prefix code, right? The way is the same, right? So basically, if it go up, or you can just pick a number here in order, and then label it, right? Okay, are we done? Yes.
With coding, like, are we just saying like n1 is like arbitrarily less than d, and so like the d minus n1 is just like the leftover codes we have from before?
I think so. Yeah. So n1 has to be less than or equal to d, right? Because it's DRE code, right? The total number of possibility of n1 is just d, right? Yeah. If we pick this number of length 1 code, and then this is the total number left, right?
I guess like in my mind, like a length, like what is a length 2 code extending another branch off of like N1.
It's extend, yeah, of course, right? N2 code will be like this,
Okay.
this, right? The tone number here is D. Yeah. That, okay, that clear? All right, so are we done? Yes, we did, right? So if on length 3 code, you not just repeat the exact same procedure, and then you'll see, basically that's why the crafting equality can be satisfied, right? It's not surprising. Okay, and then we just continue the procedure, and then we're done. Okay, and that's the proof. Any questions? Okay, good. And then we're done for the Shannon code, right? That's basic Shannon code. Okay, so now, maybe you want to look at this formula again, right? It is a very good code in general, right? We show, it satisfies the crafting equality, right? But we have a ceiling here, right? And intuitively, or, can you think an example that this code is not good enough? A simple example, I mean. Or, do you think it's a very good code? Yeah, who think it's pretty good and it's hard to improve? Nobody believes so? Yeah, then why? Yeah, it's intuitive, right? So, yeah, if, a symbol appear with a lower probability, then we just give a longer length, right? And if appear a higher probability, we give a shorter length. It's very intuitive. It makes sense, right? Yeah, okay. Yeah, let's talk about that later. So, yeah, to indicate this code is not good enough, so we're going to introduce another code, okay? So which is called Huffman code. And in your midterm, and of course in your homework, so you're gonna have definitely at least one problem for Huffman code. Yeah, it's insanely easy to construct. Okay, who heard of it? Oh, good. Oh, all of you heard of it. Do you know the story of it? Do you know how this was? It was, so Huffman from MIT, so he got this code when he was a student there. I think this is his master's thesis or a homework. Yeah, and then he constructed this code. And the surprising result of this code is that, so this is the optimal block code for any n. It's not asymptotic optimal, it's just optimal, yes.
I think the story I heard was that the professor gave the option to either like take the final or to like work on this problem. And everyone else took the final, but he like did this proof or something.
Okay, yeah. Yeah, probably. Yeah, I'm not sure exactly for the story, so it's been too long. Yeah, I was taught that like 15 years ago. So yeah, but the code is very, very powerful, right? It's the optimal code. Okay, so yeah, let's see what is the construction of it. It's very easy. So basically, the only thing we need to know is how this code is constructed. Okay, so we just need the so-called Huffman algorithm. Oh, who learned that before? I mean, who know the construction before? Only you? Okay, good.
I think we all do if we did CPE or something. It's in like DSA.
Yeah, I think they talked about it.
Which class?
Data structures and algorithms.
Oh, really? Okay, they talk about Huffman code? Interesting.
Very briefly.
Yeah, no problem. Yeah, so we're going to do this again. Or who can do it? Okay, so here, first of all, in order to construct Huffman code, the first thing is that we need to know the distribution of the source symbol, like the Shannon code. Okay, so we need to know the distribution. The Px be the PMF of x. Okay, so now we first consider the binary Huffman code, and then we're going to consider the general case. Okay, binary Huffman code. Okay, so it means that the coding alphabet is 0 and 1. Okay, and the cardinality of y is basically 2, right? D is 2. Okay, so I'll write it down in just one sentence for the algorithm, and then I'll explain the meaning of it. So what we're going to do is that we're going to order all the symbols, from the highest probability to the lowest probability, or vice versa. Okay, from the highest probability to the lowest probability. And then what we're going to do is that we're going to merge the two list likely nodes in the tree, okay? Merge two least likely nodes into one new node with probability equal to the sum of the children nodes. Okay, so let's see what do we mean by that exactly. Right, let's see an example, okay? So we consider source have three symbols, S1, S0, S1, and S2, right? And for simplicity, we just assume the probability is all the same, 1/3, 1/3, 1/3. Okay, so the first thing we need to do is that we're going to list all the symbols in this way. Okay, and we can see the probability here is 1/3, 1/3, 1/3. I mean, they're all the same, so it doesn't matter. Okay, and what we're going to do is that let's assume that we're listing them from the highest probability to the lowest probability, right? And then what we're going to do is that we're going to combine the two vertices. Let's say we have vertices, the two nodes here. Okay, and then combine that into one new node. Okay, and these two probabilities are the least, the smallest probabilities. Okay, and the probability of this new node is what? 2/3. Okay, the sum of these two. Okay, now we have a 2/3 here, and we have 1/3 here, right? So we have two nodes now. Okay, but this 2/3 is bigger, so we make it, we shift it upper, and then we make it here. Okay, so now we have this two node. Okay, and the probability of this is 1/3. Sorry, it's 2/3. And oh man, the probability of the bottom is 1/3. Okay, and then we combine them. So now we have probability 1. Right, when we have probability 1, then we're done, right? Okay, that's it. Okay, how can we assign a symbol, code symbol there, right? The way is very simple, right? So basically, you can see these two combine to one new node, right? Then we're going to assign. So we just need a rule there. So similar to the Shannon code, right? If we go up, maybe we assign 0. If it's down, then we assign 1, right? So basically, we're going to assign this as 0, this as 1. Okay, and then, so this is the second branches, right? So now we can see this is up, this is down, right? So here we're going to assign 0, assign this one, right? And then we're done. Okay, so then what is the code here? The code here is basically, so for example, for this guy, it will be this one and this one. Okay, so let's see the code here. Maybe let's see the first one. The first one here is basically, we go it from here, it's just 1. The second one is here and here, so it's 0 and 0. And the last code is, here is 1, here is 0. Okay, then what is it? So we're going to read backwards. Okay, read from here to here, so that would be 0 and 1. Right, if we read forward, then it will not be prefix. Okay, so that's how it works, right? So we combine and build this kind of tree, right? And then for the code word, we assign, just fix the rule there, and then we're going to read the code from right to left, okay, in this way to read the code. Okay, that's basically the Huffman code. Okay, we're done. So is that enough? Is that easy? It's pretty straightforward, right? Very straightforward. Okay, so now let's see the performance of the Huffman code. Okay, so basically what we need to do here is to compute the code length. Average code word length. Okay, so here for the first one, the code length is 1, right? We have 1/3 times 1 plus 1/3 times the second one, we have 2, right? And then 1/3 times 2, so if you compute it, so that's 5/3, so that's 1.667 bits per symbol, right? So that's the average length. So now let's compute the entropy, right? So here we'll consider DMS, right? So we just need to compute the entropy. So entropy is 1/3 log 1/3, right? So basically that's log 2 base 2, 3, right? So what's that? So can you compute it in your head? Yeah, that's one. Who remember it? 1.585 bits. Okay, and then you can see that this guy is a bit higher than this guy, right? But not so bad. Okay, then you may imagine, okay, so the Huffman code is, yeah, probably for performance is pretty good, right? But now, so and one thing here is that so the code length here is very small, right? So we only consider like 3 symbols here, okay, and we can we can combine them to have a block 2 code, block code with length 2, right, and so on. Then probably we're going to have a better result, right? Okay, so yeah, this is one code. So to demonstrate that, so now let's consider a more complicated example that have more code symbols. So let's see. Now let's say we have 6 symbols instead of 3. S0, S1, S2, S3, 0, 1, 2, 3, 4, 5. Okay, and then let's see, the probability distribution PMF is 0.1, 0.1, 0.2, 0.2, 0.3, 0.1. Okay, so that's a probability distribution. And okay, so now let's see how we can do it, right? So we're going to label, to order it from the highest one to the lowest one, right? The highest one is this 0.3 here, so that's S4. So S4 is on the top. And then the second largest is 0.2, right? So I have S2, S3, so make it clear. S2 and S3 here, so we write S2 and S3, right? And the rest is S0, S1, and S5. They're all 0.1, right? They're the same, so it doesn't matter. S0, S1, S2. Okay, so now we can run the algorithm here, right? Let's label the probability here. So this first one is 0.4, 0.3, 0.2, 0.2, anyway, 0.2, 0.1. Did I miss anything? Yeah, I didn't have S5. For, yeah, here. 4, 2, 3, 0, 1, 5.
There's no 0.4 probability.
Oh, yeah, 0.3, right? 0.3, 0.2, 0.2, 0.1, 0.1. Okay, very good. Okay, and then we're going to combine here, right? The first one, so we're going to combine this one to here, right? And here we have a 0.2. Okay, so now we're going to reorder it, right? So, so basically, so this will be still the same, right? And then let's see. So normally when we have a 0.2 here and then we have 2.2 here, so we put the newest combined node on the top. Okay, so we just put that on the top. Yeah, so yeah, I need some space here, so I will probably move it here. Okay. So this is our 0.2. Okay, and so now let's see. So this. Okay. So now we can see. So now we have 0.3, 0.2, 0.2, 0.2, 0.1, right? So basically, these two are the smallest, right? So we're going to combine these two. Okay, so yeah, let's write in this way. Okay, so here is 0.2, here is 0.1, right? So now we have 0.3. Okay, and then we're going. Now let's put 0.3 on the top, and then so we have this 0.3. Okay, and we have this 0.2 here, and this is a 0.2. Okay, so now this is 0.3, and this is 0.3. This is 0.2, and this is our 0.2. Okay, so now the smallest two is this 0.2 and this 0.2, right? Then we're going to combine this 0.2. Okay, so now we have a 0.4, and then we put that on the top. This is 0.4, and this is, okay, this is 0.3, and this is 0.3. Okay, and now we can see these are the 0.3, so those are smallest, then we combine those. And then we have a 0.6, and with this 0.4, okay, hopefully it works, and then we're done. Okay, and then this is 1. Okay, so this is our Huffman coding tree, and then we're done, right? So now let's label it. So basically, so let's use the same rule here. We have 0 and 1 here. Okay, and we just, if we go up, we have a 0, and go down, we have a 1. So we have a 0 here and a 1 here. Okay, and here similar. We have a 0 here and a 1 here. And then the next combine is here, right? So I have a 0 here and a 1 here. And I have 0 here and a 1 here. Hopefully it's clear. Okay, so now let's write down our code word here. Okay, let's see the code word. Let's say the first one. So the first one, here we have 1, and here we have another 1 here. Is that right? Yeah, so the first one is 1, 1. Let's see the second one here. Second one, we have a 1 here, and we have a 0 here, right? So it's a 0, 1. Yeah, the third one, we have a 0 here, and then we have a 0, right, and a 1. So it's 1, 0, 0. And for this one, we have 1, 0, 1, so it's a 1, 0, 1. And for this one, we have a 0, 0, and 0, so 0, 0, 0, all zeros. And for the last one, we have 1, 0, and 0, so 0, 0, 1. Is that right?
For the last join, the 0.6 and the 0.4.
Oh, I should flip it, right?
Yeah.
Yeah, normally the highest. Yeah. Yeah, normally it doesn't matter, but you should. Okay, I don't want to redo it, but yeah, that's why I don't have the same in my notes. But I think it should be fine. Okay, be careful here. Yeah, flip it. Add home. Okay, yeah, you can do it on your own, so I don't want to redo it, but this should be the same. Yeah, this is just, a kind of a rule, but it doesn't matter normally. So the important thing is that you want to combine the smallest two, right? Actually, where is it doesn't matter. Okay, but you should follow some rule here. Okay, very good. So now let's compute the average code length. Okay. So now let's see the first two. So but whatever you do here, so the length should be pretty much the same, right? So the number here might be different, but length is not. So we have 2 multiply 0.3 with first probability plus 2 multiply 0.2 and plus 3 times 0.2 plus 3 times 0.1 times 3, right? We have 3 of those. Okay, and then if you compute it, so that will give you 2.5 bits. Okay, so now let's double check the entropy here. So entropy is minus 0.3 log 0.3 minus, we have 2 of those. Then let's multiply 2 here. Minus 0.2 log, we have only, let's see, 0.3, we have not 2, right? Only 1. Minus, so this we have 2. Okay, and then we minus 0.2 log 0.2. Wait, 0.2, 0.1, right? It's weird what I wrote here. And then we have 3 here, right? Right? Okay, so this is what we got. So yeah, let's just compute at home. So yeah, seems it's a bit different. I don't know, but yeah. So this is what we got. Yeah, hopefully it's correct. Yeah, just double check it at home. Can you see it? Yeah, it's 2.4464. Okay, and the point is that if you see this number and this number, so you can see they are much more close than before. So one is 2.5, the other one is 2.4464. Okay, so hopefully you're convinced, right? So if we have a longer, we have more source symbols, and then the performance could be better. Okay, great. Yeah, we have 3 minutes. Let me introduce you the more general case. So this is a binary Huffman code, right? So what if we want the DRE Huffman code? Okay, so the idea is pretty much the same, right? So what we do is that we're going to merge, instead of 2, so we merge D, least likely nodes, into one node with probability equal to the sum of all the children. Nodes. Okay, so let's quickly see an example here. So let's say we have 4 symbols. Okay, so now let's consider 3 RE codes, right? So 1 is 0, 1, and 2 instead of just 0 and 1. Okay, let's see the probability here is, the probability vector is 0.5, 0.3, 0.1, 0.1. Okay, right here D is 3. Okay, so now let's construct our tree, right? Same as before, was S0, S1, S2, S3. Okay, the probability here is 0.5, 0.3, 0.1, and 0.1, right? So now instead of combining the least 2, so we combine the least 3, right? Combine all of them together. Okay, have a new one, so that's 0.5, right? Okay, then we can, let's move it up. So now here is 0.5, here is 0.5, right? Are we done? Exactly. We missed one, right? Because the DRE code, so here, every time we should combine like 3 nodes together, right? Here, we merge D least likely nodes, right? So D is 3, now we only have 2, right? So it basically means that we need one more, right? What do we do? Any idea?
Can we just make
Exactly. That's exactly what we do. So basically what we do is very simple. Exactly like what you said, right? So basically, you already know this as the code. So our symbol is S1, S0, S1, S2, S3. And we have a new code, S4. So that's a dummy symbol. Right, with probably 0. Okay? So now we can do whatever we did before, right, very easily. Okay, then we basically combine this, and that into one code. Now it's 0.2 instead of 0.5. Okay, so now we can combine these 3 all together. So now we have enough number, right? And then we have a 1 here. Okay, so now the code word is the same as the rule is same as before. We assign 0, 1, 2 here, and 0, 1, 2 here. Okay, so now the code word here is that the first one will be 0, the second one is just 1, right? And third one is 2, 0, and then 2, 1. And then 2, 2, right? Clearly, this is not useful, right? So it's a dummy symbol, then we just ignore that. And then we're good. Okay? All right, so we're out of time, so we're going to see, in general, what should we do if we do not have enough number of nodes here. Basically, we need to add dummy symbol here, right? The question is, how many dummy symbols do we need to add? Okay, great. All right, thank you. See you next week.